Yeah, thank you very much. Yeah, so today I had so much difficulty deciding what to speak about. There were many choices. Let me tell you a bit about my dilemma. So I think on the first day, at lunch, someone mentioned a Heisenberg group over lunch, which is one of my favorite groups. And this leads naturally to a particular representation of SL2 called the Bay representation. This is something that I could have told you about. That it's a wonderful representation. You should Google it maybe. And then maybe some other day, probably over some meal, we had a discussion about SL2C. And the story there, I could have told you about how it's kind of a easier version of what we've seen about SL2FP this week. And so that could have been another thing I talked about. I could have talked about what happens when you leave SL2. What does the shape look like there? And you'll see that, again, it has all the characteristics that you've already seen for SL2FP. I could have told you about relations to other geometries in p-adic geometry and arithmetic geometry, and how the Drinfeld curve appears in these things. So I decided to do none of these. But if you want to hear more about any of these things or anything that I've talked about or anything potentially tangentially related, please come find me, and also please feel free to contact me after the program is over as well. If I don't respond right away, I will get to it. And if you don't get a response from me like for a long time, just send a follow-up. You know, sometimes somehow something gets lost. So today what I want to do is to actually focus on this RT prime G that we've been talking about. And so to do this, let me first remind you what the Drinfeld curve looks like. The Drinfeld curve is defined to be all pairs xy inside FP bar, two copies of this, where xy to the p minus x to the py is equal to 1. And now one may ask, I think it's a very reasonable question to ask, why you would write down such a thing. Perhaps I won't answer that, but I'll tell you that there's another way to obtain this equation. And what is this equation? This equation is the determinant of the matrix x, y, x to the p, y to the p. And so that means that the Drinfeld curve is saying something about a determinant one set of stuff. Right, and so this makes it feel very much like an SL2 object. The equals 1 is the same equals 1 in SL2. So now what I want to do is to introduce a variant of this, a kind of fattening or a deepening of this curve. It will make it no longer a curve. It'll be something that has more dimensions. So I'll call it a variety. And this is the beginning of it. So for a non-negative integer r, consider the following thing. I'm going to take WR of any ring A over any FP ring A, and I will define this to be a truncated polynomial ring. T to the R plus 1. And so how you should think of this is that if R is equal to 0, this is the same as A adjoined T divided by T. So then there's no more T, and then it's simply A. So in R equals 0 case, you're just recovering A. Okay, so those of you who have who have some QP experience, Another way to a very closely related object that you could define is something called the Witt ring, and this is the truncated Witt ring. You lose nothing by thinking of this. So here's a definition of an R version of this thing here, which I'll call the Parahoric Drinfeld variety. So, by the way, I think as I've alluded to in over the course of this week, the Drinfeld curve is a special case of a class of varieties called Deligne-Lusztig varieties. And so in my work, I usually call this the Parahoric Deligne-Lusztig variety, but I just put Drinfeld here to remind you that this is an SL2 case. Of depth R is the following thing. It's the set of all xy inside now 2 copies of WR of FP bar, where the determinant of this thing, x, y, oh, I have some, sorry, I forgot about this. Is it okay? Sigma x, sigma of y is equal to 1. So that's the definition. And so this is the one viewed inside this truncated Witt ring. And so I didn't tell you what sigma was. So what is sigma? I guess I can do it here. Yeah, okay. So what is sigma? Sigma acts on something in WR of FP bar, which means that that's a polynomial of degree at most R that looks like this. Right, where all these A0, A1 through AR, all of these things are elements inside FP bar. And so I'm going to define sigma of this to be equal to A0 to the P plus A1 to the PT. So it's only going to act on the coefficients. And as you would expect, because of it being so parallel to our Drinfeld curve that we've been talking about this week, this also has the natural group actions that completely analogously to the Drinfeld curve case. So as in the R equals 0 setting, which is the setting of our Drinfeld curve, so maybe it's okay if I put a 0 down here to emphasize the connection here. XR has an action by matrix multiplication of some group that I'll call GR. And what is GR? GR is the group of 2 by 2 matrices with coefficients inside WR of FP. And it also has a right action by an R version of T prime, which I'll call TR prime or T prime R, whatever. And what is this? This is defined similarly. Before we had a kernel from FP squared star to FP star, and all I do here is also include this WR. So this is the kernel from WR of FP squared star to WR of FP star. Okay, and so what this means is that also analogously to our R equals 0 setting, I can define this R TR prime GR now completely analogously to how we defined R T prime G. Okay, so how does this work? I take, again, a character theta, and in my usual notation, whatever I put here is starting out life in whatever this subscript was. So this is a character of this TR prime, and this, by definition, is going to be H0 of this XR now, with some part, this part here, minus H1 of XR, with this done, plus H2 of XR and so forth. You keep doing plus minus plus minus. Now, remember in the curve case, we could just stop here because it was dimension 1, and so everything H3 and past vanishes. But now this thing has higher dimensions, so you actually have to keep going. It'll stop at some finite place. There's nothing past 2 times the dimension of XR. Okay. Okay, so at this point you should, if I did a good job this week, you'll just lap this up. But if you take a step back, you should ask why would you want to do this? Okay, so why would you want to do this? Tuesday evening at Jessica Finson's talk, she talked about how to construct some supercuspidal representations of SL2QP. And I mentioned this a bit at the end of my last lecture. So let me recall what the construction of depth 0 representations is. And where is this? Here, okay. So recipe for a depth 0 supercuspidal representation. This recipe is really simple. There are 3 steps. The first step is to just write down this RT prime G theta. This first step, RT prime G theta. And this RT prime G theta, as we know, is a representation of G, and G again is SL2 FP. Okay. Step 2 is to view this as a representation of SL2 ZP or SL2 FP bracket T, which means that you're allowed to, I mean, this is like polynomials of possibly infinite degree. And what is the map here is that you can map in this direction, and you can also map in this direction. From here to here, you just send P to 0. From here to here, you send T to 0. And then once you have this, you now have a representation of something like SL2 ZP or SL2 of this power series ring. And you can then consider compact induction up to your SL2 QP or SL2 FP prime prime T of this representation RT prime G theta. So I may write some expression like this in the future, but like this looks so funny because this thing here took up so much horizontal space. So next time I will just write compact induction of this, and then all of you will know where I'm inducing from and to. Okay, and so the recipe is that once you finish this step, you have in your hands a supercuspidal. Is a supercuspidal representation of the p-adic SL2. Okay. Okay. So here's a natural question. So maybe one answer to why would you want to do this. So there are lots of reasons other than this. This XR actually in the same way of the Drinfeld curve appears in lots of contexts in arithmetic geometry, which I won't talk about. So I'll just motivate it from representation theory. So here's a natural question. Can you get depth R by replacing, by inserting R everywhere? And what I mean by that is the following thing. Yellow is clear, yeah? Actually, are all these, just so I'm unlikely to use, is this one okay too? And this one? Also okay. That's it. Okay, so the question is, can we insert R everywhere? And And so what do I mean by that? I mean, like, we now have objects for all of these things, right? And so then this will be like join t, quotient by t to the r plus 1. And once okay, one doesn't have this map anymore. You'd have to do the bit thing to get that, but you have a map here. And then maybe an r here, and so by inserting the r's, so one will notice the concentration of new red chalk is in this first component. So all the interesting stuff is happening at step 1. 2 and 3 are automatic. So everything is in step 1. I mean, there is something to check in, not in step 2, but in step 3. But okay, so that's the natural question. How can you get depth r by inserting? Can you get depth r by inserting r everywhere? And the answer, thankfully, is yes. Otherwise, it's not a good use of 15 minutes. And this is due to many theorems. In chronological order, this is due to work of myself with my collaborator Alexander Ivanov, and actually some of these citations I'm only citing it for the most general case, and I'll tell you later the history of this, and then work of myself with Marcel Oy, and then also some recent work, solo work. Came out a few weeks ago. So let me expand out this yes. Okay, so the first thing, so one thing that we didn't get a chance to prove was why it is that RT prime G theta is most of the time irreducible. And what is most of the time, it means as long as theta is not equal to theta inverse, then this thing is irreducible. But that is something that we stated on day 1. And so in fact, the same thing is true here. So if theta is not equal to theta inverse, then RT R prime GR of theta is irreducible. And this has a kind of so this was in this form proved by Lusztig, who started considering this kind of object in many years ago in 1979, and then wrote a follow-up paper in 2004. And in the mixed characteristic setting, this was due to Stasinski in 2009, and in the kind of most general setting where we allow different what's called Parahoric subgroups. This is due to myself and Ivanov. We wrote the paper in 2019. Actually, when I was here at Princeton as a postdoc, I spent some time writing this paper. What happened after this? Okay, and then there's also we proved this under some assumptions in the general case that don't appear in the SL2 case, and in some cases this was resolved by not Dudas and me, Dudas and Ivanov. And then most recently, the most general setting that we know so far came out like 2 weeks ago. Okay, so this is an irreducibility statement. So maybe as indicated by some history, this result is much more difficult to obtain than in this R equals 0 setting. And at some point you can ask me why, but let me move on for now. But one upshot is that once we have this irreducibility result, then the argument that I told you yesterday about with this characterization on regular semi-simple elements, this thing with the Cauchy-Schwarz inequality, this thing actually goes through. So upshot is yesterday's argument with Cauchy-Schwarz inequality goes through. once you have this theorem. And so that means that, well, the result, so let me write down this characterization theorem just for, so that you can see that it's really like the flavor of things that we've been talking about this week. This is the unique irreducible representation such that the character at some special g is also going to look like this. It's going to look like 0 if g is conjugate to something that looks like A inverse inside now TR. Okay, I didn't tell you what TR is, but just believe that there's some R version of the T that we saw before. Actually, we know what that thing is. That thing, actually, you just take the multiplicative group of this. And it's going to be theta of zeta plus theta of zeta inverse if G is conjugate to this D prime of zeta inside PR prime. So you get the same thing. But on what locus? For G inside the kind of GR version of the regular semi-simple locus. And this won't really come up later, but let me just tell you, I mean, you should question what does it mean for it to be regular semi-simple inside GR. And actually actually we need something, some notion that's actually a little bit finer than regular semi-simple. And what it says is the following thing, is that now things in GR will always map to things inside G0 by basically by a similar map to over here. You send P to 0 or T to 0. And the requirement is that its image inside G0, you know what regular semi-simple there means already. The requirement is that image here is regular semi-simple. Yeah, so this is the same argument as yesterday. Okay. So now what's the upshot of this? The upshot of this is the following. So on Tuesday, Jessica didn't only tell us about how to get depth 0 representations, but she mentioned that there's a construction by JKU about positive depth representations. So what does use construction give for us? Actually, in this context, use construction starting from this data of TR prime together with a character theta will in fact produce some representation. Let me decorate this a bit. I want to call this algebraic, some algebraic construction here. And this is a representation of GR. So use construction is giving us some algebraic constructed representation of GR. So by the way, those of you who know about Bay representation, this recipe involves Bay representation half the time. Okay, so now we know that use construction will produce for us things where if you compactly induce this thing, you get a supercuspidal. So natural question is, how is my cohomologically arising object related to this thing? And one message that I've been trying to convey is that if you have two representations, then definitely one thing you can do is take its character and compare the values of the character at every single point. However, character values, this is actually usually a difficult thing to do. And one reason it's difficult is that in order to compute the trace, usually this depends on how you've come across your representation. And that means that formulas that come from geometry look inherently different than to formulas that come from algebra. And so this means that something like this, where you only have to compare on a really small locus, becomes really quite worthwhile. So a theorem here, which is obtained by applying this result to this representation here, says that R TR prime G R of theta is in fact, as a representation of GR, isomorphic to pi TR prime theta alge. Okay, so before you write this down, this is not quite true. So the first reason it's not quite true is, remember this RTR prime thing, this thing is alternating sum of cohomology groups. It's possible that this landed you the negative of an irreducible and not the irreducible itself. So I do this thing that some might find offensive. I take an absolute value of this representation. It just means this thing is irreducible up to plus minus. You just take the irreducible one. Okay, now at least we're comparing an irreducible to actual irreducible. But actually it turns out this thing is still not correct. And the reason it's not correct is for some twisting character. And this is a character that has values in plus minus 1. So it's as we heard from Jessica's talk, plus minus 1 is a difficulty historically. So one might say, okay, well, but that's a little bit disappointing because you got the one with the twist, right? But in fact, this twisting thing is a correction factor. From the perspective of putting these representations into L packets, you need this correction factor to be in there. And so, in fact, the existence of this correction factor in there is telling you that the geometry is actually picking up the correct object. So somehow, the geometry knows about arithmetic properties of the Langlands correspondence, at least the automorphic side of the Langlands correspondence. And a shadow of that is exactly this. So the geometry knows a lot more. We are trying to understand what the geometry knows. Okay. Any questions up to here? Okay, so I hope this gives you a sense of some ways in which this kind of characterization theorem is useful. Now, this characterization theorem is not it's not the first of its kind. So in the early 1990s, Guy Eniart wrote down some version of a characterization theorem for GLN QP, for some representations of GLN QP. And actually this was really important at the time because there were several different kinds of flavors of representation or constructions of representations of GLN QP. And in fact, it was because of this work that we're able to know how they all compare to each other. And this additionally has applications, or maybe applications in to establishing the Langlands correspondence for GLN. But before this, in 1965, Harish Chandra was here. Had some characterization formulas of this type for G of R, so real groups. And this was also really important for the Langlands correspondence. Langlands, who was here, crucially used this in his classifying irreducible representations into L packets. So now here's something that let me talk about a group that's not on this list. Let me talk about SL2C now. So maybe I sneak a bit of what I decided not to talk about still here is, okay, what is this thing saying? So a characterization result like this is, so one way to say is it's the unique irreducible satisfying this. Another way to say is, suppose you only knew about this function. this characterization theorem is saying that there exists a unique way to extend a representation from extend this function to a character of an irreducible representation. Yeah. So let me give me one moment to plan my board space. Okay. Okay, apologies. I will erase you right now. So another way. So maybe I write characterization theorem is saying that there exists a unique way to extend this function which function it's theta plus theta inverse taken only on the regular semi-simple part. So because you all have experience with this now, you'll be okay with this abusive notation. So one thing is, remember, not all regular semi-simple elements will conjugate into the torus that's allowed to take that you're allowed to take values in. So this means it's either this thing or it's zero. There exists a unique way to extend this function to the character of some irreducible representation. Okay, so that's another way to say the characterization theorem. So then there's a really natural question now. How to extend? Right. Okay, so let me verbally say what's something that you can do over something like SL2C, and then I'll tell you about how to do this for Q. So in SL2C, say you take a finite dimensional representation of SL2C, you can take the trace of this thing. That trace is a continuous function on SL2C. Okay, now say you only know what the values are on the regular semi-simple locus. This regular semi-simple locus turns out this is open and dense inside SL2C. And if you have a continuous function and you only know its values on an open dense locus, what can you do? You can take a limit. Yes, you can take a limit to the boundary. This is an analytic notion. This is a notion that we learned, I don't know, when in high school, yeah? And so that's beautiful, right? So this is saying that how do you extend it? You just take the limit. You take a sequence of regular semi-simple elements that tends to your thing outside of the regular semi-simple locus, and the limit of your function is going to be the value of your character outside there. Okay, but how do I do this for SL2FP? This is not so clear because now we have SL2FP as a finite set. What do you mean take a limit? They're all like, it's a discrete thing, right? And so this question is answered by algebraic geometry. And the answer is character sheaves. So let me tell you about this. Okay, so I should say, probably some of you will learn about this at some point. And what you'll learn will look nothing like what I'm about to tell you. And so my aim is not to tell you the precise definitions, but my aim is to tell you what this kind of technology can do for representation theory. So here let's return to our usual G, and with our usual G, we have RTG theta, and we also have RT prime G theta. Okay. And so basically, I mean, how you should think about this is that this RT prime, that was the link to supercuspidals. It doesn't work if you do RT, just the T1. And so that's why I made this stuff here, but it will come back. This picture involves both of them. So let's take this first, RTG theta. What's the starting data? Starting data is character theta on T. T, right? And this T is FP star. Okay. And what happens is associated to this theta, one can write down, I'll write down a fancy L with the theta as a subscript. There's something called a local system on now FP bar star. And what this local system knows about this theta. And the way it knows is through an operation called trace of Frobenius, which I'll write as sigma. So this Frobenius just means you take an element of FP bar and you send it to its pth power. But the thing is, this thing also knows about all the extensions of FP as well. So this simultaneously knows about all FP to the n at once. And how does it know about it? I'm allowed to take a trace of sigma. Turns out I'm also allowed to take trace of sigma squared. So if I take trace of sigma squared, what happens? I get some FP squared version of this. So it will give me, output for me, some character of FP squared star. How is this character related to this character? It's related in the following way that we've kind of seen before. There's a map from FP squared to FP star, and it's given by x maps to x times x to the p. And then once I'm in FP star, then I map by theta. Okay. So I will call this character theta again, even though it's not literally theta, because it has basically the same data as okay, but we can do this again. Okay. I know you see the pattern, but let me just do this. So this will be FP cubed star. This is a P cubed star, C star. Okay, and you do the same thing. So this will map to FP star. X maps to x times x to the p times x to the p squared. Okay, and then you map to C star by theta. So this L theta is a way to package together this infinite column of characters, all of which are kind of coming from this first theta. Okay. Any questions about this picture? Yeah. Sigma is Frobenius, so it's just x to the p, x to x to the p. I don't like this one. Okay. So I told you that this picture should also know about T prime. So let's do T prime. T prime is a little bit funny, right? T prime goes from the kernel, like the kernel of FP squared star to FP star, and it maps to C star. That's this guy, right? This is what I would call T prime of FP. So this is what used to be T prime, but because now I'm talking about all of the P to N's, I will modify which extension of T prime I'm taking by this parentheses here. Okay. So there's also a local system on this side. And this is also same thing, local system on FP bar star, and also simultaneously knows about all FP to the N all at once. But the funny thing is that you don't get from the right-hand side to the left-hand side by taking the trace of the same Frobenius. We're going to do something funny. And the funny thing we're going to do is we're going to trace of Frobenius prime. Okay, so let me tell you what Frobenius prime is. So Frobenius prime is going to take A inverse to A to the minus P, A to the P, like this. Okay, so this looks, I mean, you can do this. What's going on here? If you take W equals to 0 like this is an element inside the normalizer of the torus, something probably many of you computed this week. And what is this element here? This is W times the original sigma, just raising to the Pth power, W inverse. So on problem 2, there was something that connected the Drinfeld curve to things that look like BWB. And inside that problem, this kind of Frobenius shows up. So that's my Frobenius prime. So what's it doing? It's really taking A to the minus P. So this happens. And now since it knows about all P to the n at once, it's going to also know about trace of sigma prime squared. And now sigma prime squared, well, you'll notice that if I do W twice, I just get back the identity. Okay, maybe there's a -1, but let's ignore that. And so that means that this sigma prime squared is actually the same as sigma squared. On the left-hand side here, we obtain a map like this. And how is this character defined? This character is defined by mapping to this T prime of Fp. And how? I take x to x times sigma prime of x, and sigma prime of x is x to the minus P. So this is something all of you can check, that the image of this thing is exactly the kernel. Okay, so we have this now, and we can do it one more time. Let's do it one more time. Trace of sigma prime cubed. And what will I get? Well, I'll tell you what you get, and then you can check it for yourself. Which seems to be my style this week, is to give you lots of exercises during lecture. And this will map to T prime of Fp and map back. And what is the map now? The map is x goes to x times x to the minus P times x to the P squared. So you can also check that it lands in the correct spot. Okay, so the reason that I wanted to do the sigma squared, and sigma cubed is that on this T prime part, we see that sigma prime was kind of funny. Sigma prime squared, that's the same as sigma squared. So that was kind of like a T object, not a T prime object. But if you take cubed, you get back to some kind of T prime object. Okay. God. Okay, I don't yet know how much space I need, so let's see. Okay. Any questions? Yeah. Yes.
I just want to double check with the notation for the last map of like sigma from kernel. Is it from Fp what?
Fp to 6.
6. Okay.
Yeah. So it turns out in this case, you always take like the T prime of Fp to the n stuff will always be the kernel from Fp to the 2n.
So are we saying for like the middle layer of Fp squared cross, then like this is literally isomorphic to the kernel of Fp, let's say to the 4th to Fp cross?
No, I'm not saying that.
I see.
Yeah. Only the odd ones work this way.
Interesting.
Thanks. Yeah. And so what you can do is you can calculate for A and A inverse inside, or for A inside Fp bar, what does it mean to be fixed by sigma prime? What does it mean to be fixed by sigma prime squared? What does it mean to be fixed by sigma prime cubed? And that's how I'm getting these groups here. See. Good question. Yeah.
So for the even powers, is it going to go back? Like if we take sigma prime to the 4, is it going to look
Yes,
more like
exactly. Yes. Okay. So let's build a sheaf. So this local system is kind of the basic example of a sheaf. They're the ones that one starts with somehow. And so let's build a sheaf whose trace of sigma is RTG theta. So we'll not worry about T prime yet. Let's do RTG theta first. So here, what's going on? So I take RT of FP, RG of FP of theta. We learned this week what the character formula of this is. What's the character formula? So this is a representation. This is a class function. The character formula is the map that sends G to the sum over all cosets G of FP divided by B of FP, where H inverse GH is inside B of FP. And on day one, I had a map called projection from B of FP to T of FP. And this thing is given by theta of projection H inverse H. So what happens on the sheaf side? On the sheaf side, so it turns out that this kind of trace of sigma prime, this kind of thing, there's a dictionary between things that you can do in algebraic geometry and things you can do to functions. So when you do this kind of thing, projection of this thing, this is a pullback. There's a notion of pullback in algebraic geometry. This kind of thing, the sum, this is an averaging, right? There's a notion of this in algebraic geometry as well. The notion of it in algebraic geometry is push forward. So when you hear push, you hear average. Okay. So let me write down something. So I'm gonna write down something called G tilde of FP bar. And this will consist of all things G comma H B of FP bar inside G of FP bar times G of FP bar divided by B of FP bar. So a lot to write, where H inverse GH is inside B of FP bar. And one thing I can do, because everything in here satisfies this, is I can take this H inverse GH and project to something in T of FP bar. I can take this to T of FP bar by taking such a G comma H, taking this thing to projection of H inverse GH. Call this map F. It's commonly called F. But there's another thing that I can do. The other thing I can do is simply only remember the G. So only remember the G. This gives me a map to G of FP. So what I told you is that this thing is a pullback, and this thing is a push forward. And this theta and the L theta are in correspondence based on what's on this board. And so what I can write down, oh my gosh, okay. What I can write down here is I can take my L theta, I can pull it back. So L theta is beginning life here. I can pull it back to something here. And now I push along this. This is called pi. Looks fancy, but here's what's happening. Like this theta is really this theta here. This projection thing, this is the same as this map F. And this sum here, the sum, I said sum is the same as push. So actually what we see already here is that, okay, so by the thing I stated to you, that things that you naturally do in here have natural consequences over here. Actually, we already see from this point, from all these arrows, that taking trace of Frobenius gives us this middle function. Okay. And what was this function? This thing. This was take trace. Just take trace. That's taking the character. Okay. And what you can do is you can actually, in the same way that L theta knows about all fp to the n all at once, this object here also knows about all fp to the n all at once. So over there, we could take a trace of sigma squared and get the next thing. Take trace of sigma cubed, get the next thing. You can do the same thing here. What happens when you take trace of sigma squared? You will again get this object, however, not for fp now, for fp squared. And so forth. Yeah. Okay. So now the other thing you can do is this L theta worked for t and also t prime. But we had this funny thing happen that we have this interesting sigma prime. But let's ignore sigma prime for now. Let's do sigma prime squared, which we know is the same as sigma squared. So what we get there is, in fact, this thing, that if you take trace of sigma prime squared, which is the same as trace of sigma squared, actually the same reasoning that I've said over there matches this thing to r of t prime, but t prime of fp squared to g of f to this thing here. So we are getting some t prime thing, but we're only getting it at the even powers, p squared, p to the 4, to the 6. And the essential thing that happens, the reason why we don't automatically get something from a sigma prime is that this sigma prime, actually there's an extension of this sigma prime to the entire group, which says you take the usual sigma and you conjugate by w and w, conjugate by w. But one thing that you know from multiplying 2 by 2 matrices is that if you conjugate an upper triangular thing by this w, you will get something lower triangular. So it's messing up the fact that you wrote down a b there. Your b is not stable under sigma prime. And this is why it's a non-trivial statement to say what happens to the trace of sigma prime on this kind of object. And so this is a really important theorem. In this formulation, it's due to Lusztig, and it's closely related to things like Springer's hypothesis, which was proved by Kazhdan. And also nowadays, there should be a proof using 2 categories, this kind of thing. But one doesn't always have to use this. So it's the Lusztig and also Shoji. And so I guess it's kind of 2 techniques to build up the result. And this is the theorem. So A is that this geometric version of the RTG theta is completely determined by its shape on GRSS. So this feels like the characterization kind of thing, but this is not a geometric characterization thing. And in geometry, when we say something like completely determined, then oftentimes the extension, like the way you extend, is also part of the statement. And so what completely determined in this case means is the following thing, is that this thing is isomorphic to something called the intermediate extension, which is denoted by an exclamation point followed by an asterisk of its restriction to GRSS. Yeah, so this theory is due to Goreski, McPherson, and Deligne, all of whom are here. And the second thing is that if you take trace of sigma prime of this thing here. This thing is equal to R T prime G theta. So conclusion is the following thing. So first is that this thing, even though sigma prime was funny, also knows about RT prime G. So all of this RTG, RT prime G actually is falling under the same kind of family of objects. All of these things are known by this single object on the right-hand side, pi lower shrink F upper star of L theta. So I'll say Deligne-Lusztig induction is geometrically parabolic induction. So that's the first thing. And the second thing is the answer to this question. If you know there's a unique way to extend this function, how do you do it? The way to do it is to take this intermediate extension. Okay, so how to extend? Let me write it in the following way. The version of take a limit to the boundary in C for things like FP is given by intermediate extension. Okay, so two miracles. Okay, so now, give me a breather, absorb the miracle.
This case, there's
Yes.
no condition on theta, right? Like it's not.
In fact, there is no condition on theta, yeah.
For any theta,
For
even
any
for theta
theta,
equals
that's
like
right.
that.
Yeah, and then something subtle happens is that, so like say you have theta equal to the sine character, so then the representation breaks up into two pieces. Now, actually, on the sheaf side, it also breaks up into two simples. However, the trace of Frobenius will not match the character of the representation. So this like exact matching is really happening at the level of the induction, the whole induction. After you break it up, then this is something that's very subtle.
This is a very basic question, but is theta on T or on T prime, or does it not matter, or is it?
Yeah, good question. Yeah, so basically theta is whatever you like, whichever thing. So if I write it like this, then theta is in some sense starting out life on T prime.
Okay, so we were talking about different like things when we're talking about that L theta and this one.
Yes, but the L theta is something on FP bar star. So somehow the L theta doesn't know about T prime or T until you impose the sigma prime. Yeah. Good question. Yeah,
On the top one where you have the red lines.
Yeah.
The pi lower street,
yes,
I mean, the pi you had up there sends it, it's like the first projection.
yes, that's right, yeah.
But you're connecting pi lower street with like the H.
Yes, that's right. Because it's an averaging over the fibers over G. What are the fibers over G? They're the set of all HB satisfying this condition, which is exactly this index exactly. This question. Yeah.
It's still a question, but what exactly does it mean to be taking the trace of the Frobenius?
Well, yeah, this, I won't tell you. Yeah, I won't tell you. So let me end on one point here. So over here, on this side, I told you about this R version, right? And so a natural question based on me explaining this other stuff for the last half hour is how does the R fit into this picture? And that's a theorem. So theorem. And so all this stuff that I've been talking about over here also works if you put the R. after inserting R. Okay, now the proofs don't work by inserting R. The proofs are much more difficult, and they require some refinements of this picture in order to capture kind of the full theta in some sense. However, the statements do work just by inserting R. So the theorems are true after like just by modifying by R. And so what is this saying? This is saying now in the R case, this right-hand side is still something so simple as this kind of geometric parabolic induction, right? And what I'm saying is that the trace of sigma prime is going to give me R TR prime to G of theta. And what we know is that R TR prime of G of theta is giving me something that's interesting in local Langlands and compactly induces to the correct supercuspidal representation. And in particular is giving me some explanation for what use algebraic construction of representations is. So the conclusion here is that in some cases, use construction is geometrically simply parabolic induction, which is somehow like there's no twisting, there's no, you know, this funny situation where you have to do a different variety because B was not stable or anything like that. This parabolic induction is somehow what we consider the simplest possible thing. And the complicated thing is in taking its trace of Frobenius. But geometrically at the level of FP bar, in fact, use construction of supercuspidals is giving us the same thing as geometric parabolic induction. Yeah, question. Oh, no question. Okay, sorry. I thought I saw. Okay, yeah. So I will end here. Yeah, thank you very much.
Any further questions? I think.
Okay, yeah.
Sorry, I don't know if this makes sense, but this thing here is an FP bar result or a finite field result. It feels like should we be getting information about SL to FP bar from?
We are getting information about SL to FP bar from, no, sorry. We are getting information about SL to FP from an SL to FP bar situation.
Oh, it's the other way.
So yeah, this is an SL to, okay, but, okay. This thing is an FP bar thing. This thing is an FP bar thing. This thing is an FP bar thing. However, taking trace of this introduces rationality. And so then we get it related to an SL to an FP thing. Yes, good question. Yes.
I'm just like curious about like for the proof here, like with the after inserting R, how would that be different to the?
Yeah, it's really different.
Like our technique is also very different?
Yeah, technique is completely different. And so let me tell you the words. So the proof of this fact, so it turns out that this thing here, what this statement is saying is that this thing is a perverse sheaf. And what is the meaning of perversity? Perverse sheaf kind of means like that after you did this push, you didn't behave too wildly. And so in order to prove something like that, you have to control what pi looks like. And pi is something called, it's smooth and proper. So proper means the fibers are proper, and small means that there's kind of a large locus where this map actually has 0-dimensional fibers, and the part where it has 1-dimensional fibers is like controlled in some way, and the part where it has 2-dimensional fibers is even smaller, and the part where it has 3-dimensional fibers is even smaller. And so what the equations for smallness tell you is that the locus of G, where the fibers are big, is not too big. Yeah. However, if you insert R everywhere, then the fibers are no longer proper, and they're also no longer small. And so no part of that works any longer. And so to prove this, what we prove is we restrict to some nice subcategory of some nice, some natural context of this, and we prove that there's an equivalence of categories. And this equivalence of categories preserves something called a T structure, which means it sends perverse things to perverse things. And so that's the flavor of the proof. So it's quite different. It's not like object by object, it's somehow a statement about a functor.
Any further questions?
Yeah.
At the beginning, when you had the WR, I wonder
Yes.
what happens if you like the inverse.
Oh, inverse lemma of WR, you get W. That's not a good answer, but you get like, you'll get ZP, like the version of ZP. Like this is, like WR is like ZP mod P to the R.
Right.
And so you take the inverse of lemma of this, you get ZP. So you recover the whole thing, like the whole ring of integers.
So what if you use?
So the reason, yeah, so there's a good question, like, why do I truncate this thing? And the reason I truncate this thing is that I'm kind of interested mainly in the connection between geometry and representation theory, and you have to do more geometry to make sense of these kinds of things. And so my preference is to do the interesting thing at the finite level, and then later you can just you can kind of formally take this inverse limit and make sure that everything works. But there's a reverse philosophy as well. What if you start with a p-adic object that's an infinite dimensional thing over fp? What do you do then? And in fact, it's the case that these XRs are appearing in many natural constructions of this type. And then the connection to representation theory is then like, oh, well, you see this XR here, you know what's going on XR, now you know what's happening on whatever p-adic geometric thing that you started with.
Okay, there's probably time for one more question.
Yeah.
So in the theorem that like everything works after you insert R, could you explain again how that leads to the conclusion? Is there an intuitive way of saying that?
Oh, how it leads to the conclusion? Yeah, so what I mean is like you have something now that, okay, first it's completely determined by its shape on regular semi-simple locus. So it's giving a geometric reason for the characterization theorem, but also trace of Frobenius of this thing is giving the RT prime guy. But RT prime is picking up the part of the supercuspidal before you compactly induce. So this is saying that the construction of these supercuspidals is actually the same at the level of the Parahoric, this SL2ZP is the same as doing this process, which is geometric parabolic induction. Does that make sense?
Okay, let's thank Charlotte for the cause.